Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's weekly contest, kth smallest amount with single denomination combination. The problem is a bit hard, but as always, if you stick till the end, I'm very sure you will be learning at least one new thing from the video and also solve this problem by yourself. So let's get started. The problem states that you're given integer array coins representing coins of different denominations and an integer k. You have infinite number of coins of each denomination. However, you are not allowed to combine coins of different denominations. Your task is to return the kth smallest amount that you can make using these coins. So let's take an example. Let's say coins is 5 and 2, that is you have two different coins, one with denomination 5, one with denomination 2, and you have to return the seventh smallest amount that you can make using these two coins. So from 5 you can make 5, 10, 15, 20, 25 and so on and so forth. From 2 you can make 2, 4, 6, 8, 10 and so on and so forth. But notice you can't make 7 here because you're not allowed to combine coins of different denominations. So if you see, from 2 you can make 2, 4 and then you can make 5 as well. You can make 6, 8, 10, 12, 14 and then you can make 15 as well from 5 and so on and so forth. And in this series, 12 is the seventh smallest element and hence 12 is the answer, right? So hope the problem statement is clear. What is the brute force way to approach this? You know that you want kth smallest element and you can't merge coins of different denomination. So kth smallest element can be the kth element of this denomination, or the kth element of denomination of 2, or kth element of denomination of 4, or so on and so forth, right? So one of the way could be you can expand this 3. You can say you will make say 3, 6, 9, 12 and so on and so forth all the way up to 3 into k. Similarly, you expand to 2, 4, 6, 8 and so on and so forth all the way up to 2 into k, and you can expand others as well. So notice, once you have this all expanded, your answer will be one of these numbers itself, right? So what you need to do, you need to just merge all of them, remove the duplicates and then give the kth smallest element, right? That's your task. Now merging all of them, removing duplicates, let's forget about all of them. How many elements you have? Like you need at least one iteration there, right? To on all the elements, to remove duplicates, to sort them and whatnot. So in total you have n into k different elements here, right? Where n is the number of different coins you have. So you have k elements here, k elements here, k element for 4 and so on and so forth. So you will be merging them all by removing duplicates and then figuring out the kth smallest. Assume that merging and everything which just takes order one time. Even then you have to iterate over n into k element at least once. So the complexity will be at least n into k, and that itself is very huge because k is 2 into 10 raised 9. So you can't afford having k in your time complexity or space complexity at all, right? So let's try to focus on a very similar problem but a reduced version and solve that first before jumping to this problem. So the problem is exactly the same, it's just that in this version it might look bit similar to you. You have n different arrays and you need to figure out the kth largest element across these n arrays. So again, the brute force solution would be very similar. Let's say you have m elements across each of these arrays, right? So in total you will have n into m elements. So one other way would be just sort all of these and that will take you order nm multiplied by log n time, and in this, after sorting, you can just figure out the kth one and return that. So that this complexity is very huge because m in our case is of the order of k. So this is something we can't afford. Now what is the other approach? Other approach could be, okay, why even sort the entire array if we just need the kth largest one? So let's just figure out the kth or the k smallest element, and that way we don't need to sort the entire array, so we can skip some operations there. So that approach is like similar to how you perform merge of two sorted arrays, right? So here you have n different sorted arrays and you want to merge them. So one of the way could be you just figure out the smallest one that will be the smallest one across all the array, right? Now once you have the smallest one, you increment that pointer, and you have now these all elements. So from all these elements, 2 is the smallest one, so 2 will be the next larger element. So you will now remove 2 and add back 3. Now among all of these, 3 is the next smallest element, so 3 will be there. You will remove 3, add back 4, and so on and so forth. You will keep on doing this for k times, and the kth one will be your kth smallest element, right? So it's the similar thing you will do while merging two different sorted arrays. Here you have just n different sorted arrays, right? So figuring out the smallest across all these n different elements and then inserting and removing elements is something you can do using a heap or any similar data structures, right? So each of these operations of inserting and removing an element and then figuring out maximum will take you order log n time, and you will be doing it for k number of times. So overall you will require order k log n time to answer the kth smallest element. Notice in this order k log n time you have all the k elements, right? But even this will not work in this scenario because of k in the time constraint. You can't afford k at all, right? So you have to optimize this. First of all, is it possible to optimize? The answer is yes, because in this case you figured out all the k elements, right? But you only needed the kth one. So all these things that you have figured out is kind of a waste, right? So if there is a way to reach to the kth element directly, then that would save some time, and that can avoid having k in the complexity as well. So if you want to reach k directly, there is no way you can do a linear search. You have to rely on binary search, right? So now we know that we need to apply some sort of binary search here. So there are two questions: what to binary search on, and second, whether binary search is actually applicable or not in that pivot, right? So let's answer both of them. First of all, what to binary search on? So here there is not much you can do binary search on. The only thing you can do binary search on is the element itself, right? So you can say whether x is the kth largest element or not. That is what your binary search function is. Now assume x is not the kth largest element. For binary search to be applicable, you need to answer the question deterministically that whether your kth largest element lies in the left of x or your kth largest element lies in the right of x. If you can answer this deterministically every time, then binary search is applicable, right? So our new question is given set of numbers or given x, figure out whether kth largest element will be in the left of x or will be in the right of x, right? Now if you think about it, for kth largest element to be in the left of x, you need to have greater than k elements in the left, right? Then only kth largest element will be in the left of x, right? So one of the way could be figure out how many elements are there which are smaller than x across all this array, right? And let's say that number of elements which are smaller than x across all this array is s, right? Now if s is greater than equals to k, it means you have at least k elements in the left, and in that case you can skip the right half completely and only search in the left half, right? Similarly, if s is less than k, it means you have less than k elements in the left, so you can skip the left half and search in the right half, right? So at every pivot, you, depending on how many elements are smaller than x or greater than x, you can actually deterministically say whether to search in the left half or right half. And because you can completely skip one half at every iteration, you can apply binary search here, right? So we know that we can apply binary search, and we can apply binary search on the value itself, like what is the kth smallest element. Now only thing that needs to be answered is how to figure out this s efficiently, because if you can't figure out s efficiently, you can't go to left or right, or you can't decide whether to go left or right efficiently, and that will that will make the binary search slower, right? So our task is to figure out how many elements are there which are smaller than x, or smaller than equals to x, whatever you can answer, efficiently, right? Now by efficiently we mean that it should not involve k anywhere in the constraint. That's our definition of efficient for now. So how to solve this? I would encourage you to pause and try to think yourself. So the approach is, you have this n different arrays, right? You want how many elements are there which are smaller than equals to x across all these arrays, and number of arrays is short, like there is only n different arrays and n is much less than k, right? So what you can do for each of these array, you can apply binary search, right? And you can apply binary search to figure out where does x lies. So if x lies here, there are 2 elements which are smaller than x. Similarly, if x lies here, there are 3 elements which are smaller than x, and so on and so forth, right? So you can simply apply binary search across all these n elements. Each of these array has m different elements, so overall you will take log m time to converge to an index. So in this many time, you will be able to figure out the value of s, which is number of elements which are smaller than equals to x. And as we discussed, in just log some v time, v is the value or the range of x, you can converge the binary search itself. So overall your complexity would be n log m log v, where n is the number of arrays, m is the number of elements across these arrays, and v is the maximum value of kth smallest element. So that is what, or in other words, v is the maximum value across all these elements as well. That is also fine. So this is much more efficient than whatever algorithm we had previously, and this will pass the given time constraint as well. Now let's now map this to the original problem. So original problem, if you remember, had this coins array. Each of these coin, we have infinite supply, but we know that we have to stop at k. So we have all these arrays where each array is of length k, right? And we need to figure out the kth largest element itself across all these array, right? And if you apply the exact same algorithm, you will be getting n multiplied by log of m, where m is the length of the array. So here the length of the array is k as well, multiplied by log of k, or log of v, which is the maximum value. So maximum value, you can assume log of k multiplied by something which is constant, so let's say log of k. So this is the overall complexity, which is much better than anything which have k in front, right? So let's do one small dry run, and we will discuss one little edge case that is currently missing in this entire thing. So we have x as 20. So what we want to figure out, we want to apply binary search, right? So we want to figure out the kth largest element, and we currently, let's say the middle element is 20. So we are looking at 20. In other words, we need to, at 20, we need to decide whether to go left or right. That is what we need to decide. So how to answer this? So first of all, we need to figure out how many elements are there which are smaller than equals to 20, right? And how to answer this? We'll go over each of these elements, each of this array, and figure out this one by one by doing binary search over all of these. So first of all, there is no array here at all, right? This array is something we have to build. We can build using a multiples of 3, 6, 9, and so on and so forth. But that is something we can't actually build, because if you build, you will take order k time, and that will spoil the entire purpose. So this array is something, you know what will be the value, but something you can't build, right? But you need to figure out how many elements in this array are there which are smaller than equals to 20. So how to do that? The answer is, you can simply do 20 by 3, and that will give you the number of elements which are smaller than 20, right? The ceiling of 20 by 3, which will give you the number of elements which are smaller than 20. Now why that is the case? Because notice what we will do in this kind of setting. You will be doing binary search here, right, for 20. So let's do the same thing. Let's assume that you are doing binary search here. So binary search in the range 0 to k. So you land at some index I. At this index I, you need to decide whether to go left or right. So how to decide that? You need to first see whether this element is smaller than 20 or not. What will be the value of this element? This element value would be 3 into I, right? Because the ith element would have 3 into I as a value, right? Or 3 into I plus 1, whatever, how you index that depends on that. So let's assume that it is 3 into I. So if 3 into I is greater than 20, you will go in the left side of it. If it is less than 20, then you will go in the right side of it. Sorry, if it is greater than 20, then you will go in the left side. If it is less than 20, yes, you will go in the right side, right? So if you keep on doing this, where, like, what do you think, where you will end up, which I you will end up having? It would simply be, you want a index I such that it is less than equals to 20, and you want maximum of this index, right? So I should be less than equals to 20 by 3 itself, right? And because I is the index, that will be the number of elements as well, right? So that's like simple proof why 20 by 3 as well work. You can prove it in other ways as well, but simply you don't need to apply binary search here. Instead, whatever the value of x is, you can simply divide it by 3, and that will give you number of elements which are smaller than 20 in this array. So in this particular case, there are 6 elements which are smaller than 20 in this array. In this array, there will be 10 elements which are smaller than 20, right? 20 by 2. In this, you will have 5 elements which are smaller than 20. In this, you will have 2 elements which are smaller than 20. In this, again, 2 elements smaller than 20, and in this you have 4 elements which are smaller than 20. So in total, you have 4, 2, 6, 2, 8, 5, 13, 13, 10, 23, 23, 6, 29 elements which are smaller than 20, and you are looking for 12th smallest element. So obviously 29 is much greater than 12th, so you will search in the left half itself, right? Because you are saying that there are 29 elements here and you want 12th largest, so you will search in the left half. Now there is a catch. The catch is, what about duplicates? Notice you will have 4 here and you will have 4 here as well, but you don't have to make or count 4 twice. So this 5 includes 4 and this 10 includes 4 as well. So you have to count 4 exactly once, right? So you need to remove duplicates as well from this 29 elements, and after removing duplicates, if it is still less than 12, you will go in the left side or you will go in the right side. So this 29 is something that involves duplicates, and you need to remove duplicates here. And that's the last trickiest thing in the problem. Let's focus on this smaller problem again. The problem is, forget about all of these, right? Let's say you just have two different arrays, right? 3 and 2, and you need to figure out how many elements are there which are smaller than equals to 20, and you want to avoid all the duplicates that is possible, right? So in the first one there are 6 elements which are smaller than 20. In the second one there are 10 elements which are smaller than 20. Now you have total 16. You have to subtract the duplicates count here, right? Now how many elements will be there which are duplicates? The answer is whichever occurs in both will be duplicate, right? So what occurs in both? That is the LCM of both. So let's figure out the LCM here. LCM is 6. So whatever will be in the multiple of 6 will occur in both, right? So LCM is 6. Now how many elements are there which are multiple of 6 and are less than 20? Answer is again 20 by 6. You will get 3. So there are 3 elements which are smaller than 20 and are a multiple of 6. So in total there will be 13 elements, 13 unique elements which are smaller than equals to 20 and which lies either in the first or in the second array, right? So once you get this 13 for this 2 array, you have to do the exact same thing for, let's say, 3 array. So if you have, like, let's say 4 as well, then everything will change, the equation will change. Why? Because now not only you will have intersection across more than 2 things. For example, if you have these 3, let's say, so number of elements which are smaller than equal to 20, here is 6, here it is 4, and here it is 5, right? So in total you have 21 elements which are smaller than equals to 20. Now sorry, now notice there will be something which is common across these two but not present here. There will be something which is common across these two but not present here. Now there will be something which is common across these two but not present here, and there will be something which is common across all these 3, right? So you need to make you need to consider all of these scenarios while you are considering while you are counting the number of unique elements, right? And if you think closely, this is exactly similar to the set problem that we used to have in our 11th 12th mathematics. So let's say you have this A and B. What we want here is to figure out the union of A and B, that is how many unique elements are there across A and B, right? And how we did that? We figure out the number of elements in A first, we figure out the number of elements in B first, and then we subtract the number of elements which are common across these two, right? That's what we did for the first, when only 3 and 2 were there, right? And we get this particular formula for everything in A and B, right? Now if you want to do the same thing for A, B and C for 3 different elements, the formula will change slightly. You will have to subtract this common area, you will have to subtract this common area, right? Notice that you have subtracted this common area twice, right? So you have to add back this common area again, and you have to also subtract this common area, right? So basically you have to subtract all the common areas and then you have to add back this, because you have subtracted this more than what it requires. So overall what you will be doing is A plus B plus C, and then subtracting all the 2 order intersections and then adding all the 3 order intersections, right? Similarly, if you have A, B, C and D, what you will do is there will be D as well. What you will do is you will add all the individual contributions, then subtract all the second order intersections, then add back all the third order intersection, and then subtract all the fourth order intersection. And you will keep on doing this for whatever number of elements you have. So if you generalize this, what will it be? Add all the first order, add subtract all the second order, add all the third order intersection, subtract fourth order, add back fifth order, and so on and so forth. So if you have n different elements, you will have 2 power n minus 1 different expressions in this particular formula, right? So in this case you have 3 elements, so you have like 1 2 3 4 5 6 7, which is 2 power 3 minus 1 expression, right? Similarly you have 2, so you have 2 power 2 minus 1 expression here. So if you have n different sets, you will have 2 power n minus 1 different expression, and which one will be minus, which one will be plus, that depends on the number of things inside this. So if you look at A, C and D, you know there are 3 elements here, so this third order or the odd order will be added and the even orders will be subtracted, right? So to figure out the intersections across all these things, you need to go and figure out the value of these 2 power n minus 1 intersections. Now from these 2 power n minus 1, individual ones you already know of, right? You already know the value of A, B, C and D. That is simply 20 by 3, 20 by 2, 20 by 4 and so on and so forth. Now you want A and B, let's say. So what you will do, again, we want something that should occur in both A and B. That is a multiple of both 3 and 2, which in turn means that is a multiple of 6, right? So basically whatever intersections you want, you can simply take the LCM across all of them and simply do 20 by that LCM, and that will give you the total value or total count of that particular expression. So in this case, if you want to figure out A, C and D, let's assume this is D. So what you will do, you will figure out the LCM of 3, 4 and 8, and if you figure out the LCM of 3, 4 and 8, it will be 24. So you will simply do 20 by 24, and that will be the number of elements which is common across all these 3, right? So figuring out LCM is simple. You can LCM is nothing but product by GCD, right? So GCD is something you can figure out easily, right? You know how to figure out GCD efficiently using recursion, right? So you can figure out GCD easily. Once you have GCD, you can do the product of all the elements, you can divide them, and that will give you the LCM. And once you have LCM, you can divide it by the X, and that will give you the count of that particular expression, right? So what is the overall algorithm now? You will first do a binary search on X, so that will take you order log V time. V is the maximum value that is possible. Now for each X, what you need to do, you need to figure out how many elements are there which are smaller than X across all these denominations. So, and you want unique counts, right? So for that, you need to figure out the value of all these 2 power n minus 1 expressions. So first of all, you are figuring out something for 2 power n expression. So let's add this. Now what will be the value for each of this expression? Let's talk about ACD. So you have to first figure out their product, right? So figuring out product will take you order n time because there are n elements, right? You have to figure out the GCD as well. Now GCD will also take log n time. So let's add n log n again here, right? Now this much time you will figure out the LCM, and once you have LCM, you can divide it by X to get the count. So you will do this for all the 2 power n combination, and this will be your overall complexity. Now will this pass? The answer is yes, because V is very small, like this multiplied 25, so V is of the order of 30, right? So log V is of the order of 30, 2 power n is 2 power 15 here, and then here it is 15 multiplied by something, so again of the order of 15. So this overall will pass the given time constraint very easily, right? So hope this entire solution is clear. If you have watched to this point, I would strongly encourage you to pause and try to code this entire thing by yourself, because that's the most important thing you should do while observing. So next, looking at the code. The code is exactly what we just discussed. We are doing a binary search for the kth largest element. Now we simply figure out if number of elements is smaller than the middle element. If it is greater than or equals to k, we will search in the left half, otherwise we will search in the right half, right? So now let's look at the count smaller. Count smaller, basically we are iterating over each of these expressions. Now iterating over each of these expressions is something you can do using recursion, or if you are aware of a bit of bit masking, you can do using bit mask. If you are not aware of bit mask, I have already explained that multiple times in this channel. You can watch one of those videos. I will try to link one of them. So here you are iterating over all the bit masks from 1 to 2 power n, and as we know, we need to figure out LCM of all the numbers involved here in this expression, and then we will do x by LCM to get the count. Now we need one more thing, which is whether it is subtract or added in the answer. That we can figure out depending on which order expression it is, or how many sets are involved in this expression. So this count will denote the number of sets involved in the expression. So if count is even, we will subtract. If it is odd, we'll add. Now only thing how to figure out this LCM and count, we will iterate over all the elements. For each element, we will see if it is present in the set or not, in the current expression or not. If it is present, we will increment the count, and we will like this is the first element. If this is the first element, we'll simply assign LCM to that. But if it's not the first element, we know that LCM would be LCM would be product divided by GCD. So product is this number multiplied by the current number divided by GCD of this number and the current number, right? So once you have answer, once you have this LCM, you will just divide it by x and add or subtract based on the order of expression it is. So hope this entire solution makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Thank you.